Thank you so much for joining us. And I'm going to let Brian from PG&E take it away and talk some little introductions to our efficient HVAC and dehumidification strategies for craft cultivation operations. Thanks, Brian.
Hey, good afternoon, everyone. My name is Brian Collard. I'm the HVAC program coordinator for PG&E. I have the pleasure, first of all, can you hear me? Carmen, can you hear me?
Yeah, absolutely.
Okay. For some reason, I cannot turn on my screen. Hold on for just 1 second. Oh, thank you so much, Carmen, for that. Appreciate it. All right. Good afternoon, everyone. My name is Brian Collard. I'm the HVAC program coordinator for PG&E. I have the pleasure of being able to offer these classes and help put them on. So thank you very much for everyone's attendance. Let's go over a little bit of housekeeping, some safety. So first of all, at PG&E, we take our safety very serious. So please speak up for safety. Several of you may be working out in the field in different facilities. If you see something, say something, speak up for safety. It's important. Make sure that you or maybe a colleague gets home safely to their family. Next, please take care of yourself. Remember to stretch and hydrate during the course of this presentation. Please follow good ergonomics. At least for me, most important thing here is posture. I throw a pillow behind my back. It causes me to sit up a little bit straight. So maybe something that you want to do. But keyboard position and also screen height are very important. In the event of an emergency, we are going to call 911. If you're calling in from California, this is earthquake country. Please remember, drop, cover, and hold. Meaning we're going to drop under a heavy piece of furniture like a table, a desk, or something of that nature. You're going to cover your head with your arms and hands as much as possible, and then hold in place until the shaking stops. Unfortunately, in today's times, we have to talk about active shooter. In that event, we're going to get out, hide out, or we're going to take out that individual. Please remember your evacuation plan and path of egress out of your home, making sure it's safe for you to exit. And then hopefully you have a place to meet in the event of an emergency. Back up 1 slide, please. I have one more statement. Please. At the bottom there, highlighted is something very important. Please call 811 before you dig. This is a free service offered by all the utilities. When you call 811 before you dig, you're going to provide pertinent information, name, phone number, address before you dig in the ground. Those are key words. And then what will happen is you'll have, utilities, things of that nature showing up at your property to make sure it's safe for you to dig in the ground. They'll mark out the line. So please call 811 before you dig. And next slide, please. Go bags are very important, especially with some of the events that we have in California. Imagine being asked to evacuate. Such was the case last year with South Lake Tahoe due to some of the fires that we had. It actually entered the basin. And so imagine asked to be evacuated. You don't have, for example, your heart medication. That's a prime example of what you would want in a go bag. So there's a reason why the military has bug out bags. This is a prime example. You want water, food. If you got furry ones running around like I do, pet food is essential. Cash, credit cards, just the essentials to get you through if you're ever asked to evacuate. And next slide, please. This is being recorded. We do not have the permission as of yet to release, but that will be coming soon. This should go up as on demand, so look for that in the near future. But this is authorization for recording and release of this content. So please remember that during the course of this presentation. And next slide, please. This is our disclaimer. During the course of this presentation, there may be different products and manufacturers shared. Please keep in mind that those products or manufacturers, we're not stating that you have to use those products or manufacturers. We're not endorsing any one product or manufacturer. So please remember that during the course of this presentation. And next slide, please. This is my QR code. You can scan this with your camera phone. It will rocket you into the 4th dimension. Now, this is access to 60 plus classes on anything and everything HVAC. I try to get involved as much as possible. And for example, so we're leading the state in providing cannabis classes. So that's what you're seeing today. So thank you very much for joining. And I believe that is plenty out of me. And I'll turn this over to Carmen.
Yeah, thanks, Brian. I really appreciate it. So, just going to introduce what we're going to go through today. If you can drop in the chat what you're hoping to get out of this presentation, that will help us kind of cater as we go. So if you want to drop in the chat or drop in the Q&A, what you're hoping to get. And then today we're going to cover a little bit of our introduction, what we're doing now, and then a little bit of HVAC 101, system types for craft scale, commissioning and maintenance, common mistakes, and then we'll talk about some tips and tools, and then we'll go through a Q&A. So I'll be turning things over to Jim. Jim is going to be giving us our full overview, and then at the end, we're going to have some Q&A with Dan and Josh. So Jim, if you want to introduce yourself, and then Dan and Josh after that.
Yeah, thanks, Carmen. Jim Megerson. I'm a licensed professional engineer. I've been in the industry for 35 years, focusing in cannabis since about 2017. Have done well over 30 cultivation manufacturing facilities in about 10 different states, accounting for nearly 1 million square feet of operating buildings out there. Dan, you want to introduce yourself?
Lesson number one, always unmute yourself before you talk. Hey, I'm Dan Dettmers, senior application engineer with Quest Dehumidifiers. But I'll expand that comment. We're owned by a company called Megerson Industry that also owns brands such as Agronomic IQ, Cultiva, Novel Air, Conviron, Argus Controls. I represent quite a few different manufacturing sectors of HVAC equipment serving the cannabis industry as well as the rest of the CEA industry, or CEH. I'm sorry, we're talking to California here. Personally, I've got about 25, maybe a little more years in HVAC and industrial refrigeration, spanning everything from residential, commercial, industrial, food processing, pharmaceutical. My personal history is I started with a Cannabacia family in about 2007, growing and processing hops. Moved over to cannabis and indoor gardening about 6 years ago. I've seen quite a bit, we'll say that. And Josh, your turn.
I'm Josh Gerovac. I've been working in the regulated cannabis industry in California for the past 6 years. Prior to that, I was working with a company called Fluence Bioengineering as a horticulture scientist. Received my bachelor's and master's in horticulture from Purdue, and really passionate about just efficient operations, and yeah, excited to be part of that panel here.
Great, thanks so much for introducing yourselves. If you go to the next slide, the learning does not stop here, so this will be posted as an on-demand so people can watch it, but you can also look at all the other previous workshops in this series by going to our catalog here. The /California will take you to all the California relevant ones. If you just go to our catalog as a whole, there's tons of on-demands, both this series as well as other series. So go to the virtual classroom, check that out, and then I'll turn it over to Jim, who is going to be our teacher today.
Great, thanks, Carmen. Did you announce this poll alert, Carmen? What is a typical size room do you work with in canopy per square feet, or canopy square feet? This kind of gives us a feel for where some of our audience is working from.
And while we're doing that, I'll just, for Jim's sake, since he can't see, those of you who are throwing in items in the Q&A, continue to throw it in there. I'll answer as I can, but most of you have commented that you're looking to learn how to design efficient systems for small cultivation, and congratulations, you found the right place. That's exactly what we're talking about today.
So just looking at the California license sizes, there's specialty cottage, specialty, small, and medium. And I think most of what we're talking about today is probably going to be focused at folks that are at that 10,000 square feet and below for the most part. So let's just kind of, one of the things that I always get asked about is, how do I get started? And it really starts with the business plan, and the business plan dictates everything. Looking at how much revenue you want to do per month, that leads to maybe how many pounds per month at your current, wholesale price, leads to grams per square foot, leads to size of canopy, number of benches and racks, the size of the room, number of flowering plants, and number of bedrooms. So, it really all starts at the plant, at the business plan, and then it starts at the plant and works its way out. Once we get to the canopy size, then we can determine the size and the number of the rooms, what those watering rates might be, what the number of lights are, and then that leads to how we might handle some of the HVAC and dehumidification needs, electrical service, equipment locations, and structural concerns. These are all things that you need to be thinking about when looking for or building new real estate for these buildings. So let's get into some of the specifics here. So let's start talking about cooling loads and how that affects the space. So when you're talking about a typical building, a school, a church, a retail space, the type of loads that we have in those spaces are envelope. We have envelope heat gain. That's the heat gain that we have through the roof and through the walls and the windows. We have heat from people. We have heat from lighting and computers and printers. And then we have the ventilation load. Code requires us to bring in so much outside air into the building to ventilate the space. And so you have all those loads that affect the space. Well, when we're dealing with indoor agriculture or controlled environments for agriculture, it's much different. The envelope loads are much lower. Usually, if you're running at an energy code wall, plus if you're using insulated metal panels with R20 walls, we really don't have a lot of the outside temperature that affects what's going on inside that space. The lighting is it's much higher than normal. We're in an office space, you might be at 1 watt per square foot or less. In a grow facility, and you could be 30 to 50 watts per square foot. So it's significantly higher. And then we have plants. Our plants are our occupant, not people. And in the plants, we use water. We give our plants fertigation so that we can deliver, nutrients to them. And so that water that goes in has got to come back out of the room somehow, either through runoff or it has to come through the plant. We have much fewer people per square foot. We're really not concerned with controlled environments for people at this point. We're really looking at the plant. The paradigm in all this is that what we're doing is we're designing and developing and building life support systems for plants. Without the proper amount of light, the proper amount of nutrient delivery to the plant, the proper CO2, all of those things, that the plant will not live. Ventilation in these spaces are kept to a minimum because typically we are augmenting the CO2 in the space. So outdoors, you may typically run between 500 and 700 parts per million. And if you're trying to keep between 1,200 and 1,500 parts per million, you want to bring as little outdoor air into that space as possible so that you're not diluting that CO2 with a lower concentration. I typically tend to bring a little bit of air into that space just to keep that space pressurized positive to other areas. But when you really come down to it, it's all an energy balance equation. We're just trying to either remove the heat that's in the space and replace it with colder air and drier air so we do the proper amount of cooling and dehumidification that's needed in that space. Talk about the moisture removal piece of this a little bit. So many of you may be familiar with the term transpiration, but that is the amount of moisture that we put into the grow medium is saturated with nutrients, and those nutrients need to be delivered through the plant. I don't know about most of you, but and maybe I'm just a little bit more simple-minded, but when I was in high school and took biology class, I always thought that plants sucked water out of the soil, and they don't do that at all. the water that moves through the plants is moved through hydraulic pressure, the higher pressure in the grow medium versus the pressure that's in the air. And we'll talk a little bit more about this vapor pressure deficit, but it really is a difference between the pressure in the soil versus the pressure in the air that moves water through the plant that delivers nutrients to the plant. That water that leaves the plant through transpiration comes out of what's a stomata. You could think of that as like a mouth on the plant, and they usually reside on the bottom of the leaves. And water comes out of that, and oxygen comes out of it, and then CO2 is taken through the stomata into the plant. The other evaporation that occurs in the space is also what comes out of the grow media itself, just through natural evaporation. And so all of that together, the transpiration in that is the evapotranspiration. And why is this important? Because this is how the plant receives the nutrients, period. Temperature and humidity drives nutrient delivery to the plants. Without that, the plants wouldn't receive the proper amount of nutrients that they need. So let's talk about the vapor pressure deficit. And I'm sure most have heard this term a lot, but it's basically the difference in the pressure at saturation at the leaf versus the pressure that's in the air. And if we don't, and to maintain the proper difference, VPD is different for every plant at the optimum level. And that's to optimally move nutrients to that plant. With cannabis, you know, a mother and a veg, it's between 0.9 and 1.1 kilopascals. And with flower, it's between 1.1 and 1.4 kilopascals. And relative humidity and space temperature affect what that VPD is, and the temperature of the leaf as well. So you can see this is a chart. This is a VPD chart, and you can see here at 70 degrees temperature to be at a 1.3 for a flowering plant, you would need to be, oops, I lost my cursor. At 70 and 1.3, you need to be around between 42 and 40% RH. That VPD may change. You know, if you're at 82 and 58, that's 1.3. So you can hit you can hit the same VPD at different temperatures and humidity. So, well, what's the conundrum about the load? Why is the load? Why is that so hard for us to handle with conventional HVAC equipment? Well, the problem is that when the plants are small, when they first go into flower, they're small and they're not transpiring as much. And as they grow, they start transpiring more. Well, there's another thing that's happening inside that space as well, and it's called evaporative cooling. And as the plants release that water moisture into the space, it tends to cool the space. It doesn't tend to, it does cool the space. And many times it can be as much or even more than 50% of the lighting load in that space. And in many cases, well, not in many cases, but in some cases, I've actually seen where the sensible load in that space is actually negative, where we've had to deliver warmer air to the space to maintain the temperature. So I've actually seen at 82, if my set point is at 82 degrees at full transpiration, I've had to deliver 84-degree air to that space just to keep it at 82 because the amount of sensible, the negative sensible that's in that space. So as a plant grows, there's more water and more transpiration, and there's a higher latent load, and there's a little sensible load. So we need to have systems that can really adapt to that very quickly and easily. And that's a difficult thing to do. That is the conundrum in itself. So we have a poll result, another poll alert here. Cameron, did you get any results from the poll?
Yeah, let me just share those results. It looks like most people are working with slightly smaller room sizes. Or sorry, slightly larger room sizes. So
Yeah,
mostly greater than
larger.
1,000
Yeah.
square feet.
Great. Yeah. All right. So let's start talking about the different types of HVAC systems that we might find in a craft grow. And to kind of categorize those, oh, this is another poll alert. So what kind of HVAC system do you work with currently? So do you have packaged air conditioning with dehumidifiers? Do you have split systems with dehumidifiers? Or do you have integrated HVAC, which is basically a unit that will do both cooling and dehumidification? And then others or unknowns. And we'll get to those results later. So let's talk about some different systems, and we'll try to define those as we go. So basically the application is plant life support systems, and we need heating, ventilation, air conditioning systems that will adapt ourselves to this environment. They must be able to do high moisture removal rates. And they must be able to do a significant amount of air changes per hour. They need to deliver air above the space dew point. And this is really something that's very important to me to try to emphasize when I talk with folks, is that we really want to deliver the air above space dew point. And if I'm trying to replicate what Mother Nature is doing outside, if I'm trying to keep the space at 82 degrees, well, if you're outside and it's 82 degrees, what's the temperature of the air that's blowing around? It's 82 degrees, right? So why would I want to deliver 55-degree air to a room that has plants in it, or anything, you know, colder than that? So we want to try to replicate what's going on outside. So if we're at 82 degrees and 60% RH, that's going to dictate a dew point of about 67. So you're going to want to deliver the air, and my rule is 2 degrees above dew point, just because I don't want to condense on anything in the space that might be colder, because I'm blowing cold air onto it and causing it to sweat. These systems need to react to the changing load conditions. Like I said, the conundrum is that the load is changing all the time. As a plant grows, the load changes. So it has to be something that will react to that changing condition that's happening all the time. And it really should be built to run 24/7. I mean, these systems, they don't run, you know, like an office building, you know, it's occupied from 8 in the morning until 5 in the afternoon. You know, our spaces are occupied all the time. The plants are in them all the time. It's not people go home so we can turn things off and let it rest. So it needs to be built to run that way. And then, of course, we want to be energy efficient. You know, not only are there some states that are regulating that, including California with Title 24, but, you know, to add more to the bottom line, it would, you know, to reduce our costs, we want to be energy efficient. Well, that's a lot of tall orders of things to demand out of our HVAC equipment. So let's talk about different types of systems that we might see in a craft grow. There's basically two different types. There's decoupled and then there's integrated. A decoupled system is a system that uses cooling, uses part of its system to just do cooling, so to take care of cooling for the lights. And then the other part of the system would be for dehumidification. And you can kind of see, I've got some images up here on the top right, which show some, you know, split systems and dehumidifiers. And so we can use those both in conjunction to maintain temperature and humidity in the space. Or you might find yourself using an integrated heating, ventilation, and air conditioning and dehumidification system. And what it does both the dehumidification and the cooling all in one system. So it usually has some sort of reheat, so it subcools the air down to get the moisture out of it and then reheats it back up above dew point. So let's just talk about what hot gas reheat is a little bit. And to do that, we'll talk about, you know, a very simplistic, you know, diagram here of the refrigeration cycle. As we have, you know, colder refrigerant is going to go through our evaporator coil, and then it's going to go through the compressor. The compressor is going to compress that liquid, causing it to be superheated, and then send it through the condenser. Like your outside condensing unit, this is a typical condenser. And then that hot superheated liquid goes back through an expansion valve, which cools it back down rapidly and sends it back through the evaporator. So in a simple arrangement like this, you're seeing that we're sending that out to the condenser to be cooled down. So this condenser is cooling some of that superheated vapor back down with the condenser before it goes through the expansion valve. Well, instead of sending it out to the condenser, what we can do is we can send it into a coil that's in the airstream and allow that airstream to cool that air and have that heat go back into the space. So where air is cooled down to its dew point, the water condenses on the coil, which is your condensate. It goes to the compressor. Compressor adds heat to it. That goes into the reheat coil that then goes back heat into the space. So we're cooling this down, sometimes to temperatures around 48 degrees, and then reheating it back up to above dew point. So let's talk about how some of these decoupled systems might be arranged in your space. I have two different examples here at the same facility, but this was used to show the customer what our options were on option 1 and 2. And so we're using typical DX cooling for our sensible loads. That's these split systems that I have highlighted here in blue. And then we're going to use dehumidifiers to remove the moisture from the space. Something to keep in mind is that in addition to our lights, these dehumidifiers are also going to add heat to the space that we need to take care of. And depending on their size, it could be anywhere between 6,000 and 24,000 BTUs of cooling that will be needed to remove that heat from the space. The disadvantage of this is that the air that's leaving these split systems is going to be typically right around 55 degrees. And as I mentioned before, you know, the optimum temperature would be a couple of degrees above dew point. So that air really needs to be mixed into the space, either with fans or that heat directed so that it is blowing directly and colliding with the air coming from the 55-degree air system. The other thing to be important to know is that if you were going to duct this system like it's shown on the left, you probably wouldn't want to use metal duct because that duct work would sweat in the space. So many people will use fabric duct for that. Or you could look at the option on the right and not use any duct at all, and then just blow into, you know, high velocity fans and try to mix all that air up into the space. This isn't very energy efficient. Obviously, you're doing some dehumidification and adding heat back to the space, and then you're having to cool it back down. So you're usually going to have a little bit more tonnage involved here than what you might be if you were if that was in the airstream. These systems are higher in maintenance. The split systems are not built to be 24/7 capable. The dehumidifiers likely are, but not the split systems. But it is a lower first cost option, and works well. You know, I would say in 1,000 square feet and below.
I'll just throw in to reemphasize the point that Jim made. The air circulation and how you have everything set up is pretty crucial to the efficiency of the system. A lot of times we'll see, for example, air conditioners blowing right into the intake of a dehumidifier. Well, that's cold, dry air that you're blowing into the dehumidifier, which really wants the warmest, most humid air possible. Other times we'll see circulation fans going in every which direction, blowing air away from intakes of the air conditioner dehumidifier. Take a step back, take a holistic look at your entire layout, make sure your circulation fans and all of your other equipment is working in harmony. You know, you need the movement on the plants, but at the same time, get everything mixed up nicely so when the air does touch the plant, it's not really dry, warm air from a dehumidifier or really cold, humid air out of that air conditioner, and you don't have things fighting it against each other. That's probably the easiest way to and quickest way to boost efficiency in a system like this.
Yeah, thanks, Dan. Appreciate that. Another way of arranging this, which I prefer and try to do if I have the space to do it, is this is a controls diagram here, but it kind of demonstrates what I'm trying to accomplish. So I have my air handling unit here that goes out to a condenser. That's my split system, if you will. And then I do what's called a side stream dehumidifier on the return going to this unit. You'll see that you might have multiple dehumidifiers depending on how much moisture you need to remove. But the good news is that this warm air coming off this dehumidifier is going to mix with return air from the space before it hits the air handling unit. And then it's going to get cooled back down. Now, in many cases, what you might need on the discharge is some more heat to get that up above dew point. In this particular case, it was an electric heater. In California, you wouldn't do that. You want to use hot water or some other means of heat. But this method works very well and has very good control. And you're doing all your air mixing back here before it hits the air handling unit. You'll see a heater that I've got in here, and I'll talk a little bit about that later, but that is if you were going to use the same arrangement in a dry room. And I'll talk about that later.
I'll just throw in a comment for all the engineers on here. I know a lot of you who do traditional commercial buildings are probably freaking out at this design because you're taught don't put the dehumidifier before the air handling unit. You're just taking out moisture that the air handling unit would have normally taken out. My answer to that is in this case, remember, you're talking about a room with a sensible heat ratio of 0.6, 0.7, right? Your latent load is so huge that there's plenty of moisture to go around for all the equipment to take out. So this is a really good configuration for dehumidifiers in a grow room because it removes the moisture and then the temperature added by the dehumidifiers is taken out by the air handling unit so you can get better control over the leaving conditions.
You know, the other thing too that I might mention, Dan, that be very careful how you look at this. This dehumidifier is in parallel with the air handling unit. It is not in series. These dehumidifiers, you can't take the return air straight through there and blow it straight into the air handling. That's why it's called a side stream. I'm pulling air from the return and then putting it back into the return. It's a lot different than if I was bringing all the air through the dehumidifier, because the CFM of the dehumidifier is less than what the total CFM is going through this duct. That's another thing to point out. Because I've had somebody actually hook this dehumidifier up in series because they didn't understand what was being directed, and it burned out the motor of the dehumidifier, the fan motor. So you might want to make sure that that does not happen. When you're looking at an integrated HVAC system in D, this is usually DX with hot gas reheat. And so it's kind of the diagram that we've shown before. What's important is that you probably are going to end up with a 6 or an 8 row DX coil. You really want fully modulating hot gas reheat. And I'll talk a little bit more about that here in a minute. You'll want at least one of the compressors to be fully modulating so that you can have variable capacity control of your system. It's capable of this. Usually they're capable of discharge air temperature control. You can either get them in air or water cooled units. And there's all manufacturers. There's multiple manufacturers that make these, and they are generally very energy efficient, and they're very 24/7 capable. They are a higher equipment cost, but they have generally a lower installed cost. Now, I will say, you know, not all hot gas reheat is the same, and you really need to investigate this with your manufacturer. You know, some of these manufacturers have what's called a dehumidification mode, but they don't really operate the same as what this unit does. They go into a cooling mode, they look at the temperature and they say, oh, well, you want it to be 77, but it's 82 in the space, so I'll go into cooling mode. And then they will provide cooling to the space. And then once that set point is met, then they'll say, oh, well, the humidity is higher. So then my set point, so I need to go into a dehumidification mode. And so they go into dehumidification mode where they use the hot gas reheat. and they could be going from sending, 55-degree air to the space to sending, 85-degree air to the space next, or maybe even 90, depending on the unit. So you really want is a unit that cools that air down coming off the evaporator coil to around 48, sometimes as cold as 43 in some cases, and then taking that hot gas and reheating that air back up to above dew point, which is around 67 or even 70 to the space. And so you're delivering a consistent temperature to the space. You're not varying that temperature greatly. So you just have to make sure that you truly understand what the manufacturer is providing. A good example of that is this particular unit. You can see my set point here going across for temperature, and then this is my relative humidity set point down here. And you can see that lights are turning off and then lights are turning on. And you can see how this unit cycles off and on. And this is a typical HVAC unit with hot gas reheat that doesn't have supply air temperature control capabilities. And you can see how it modulates, much like a heartbeat going across here. It's very inefficient. This is when the compressor kicks on, the compressor kicks off, compressor kicks on, compressor kicks off. And if you were able to drill in deep into this, you'll see that this is about a 10 to 20 minute, well, from peak to peak, it's 20 minutes. From peak to valley, it's 10. Well, that's because on this particular unit has a 10-minute compressor safety on it. So once the compressor turns off, it won't let it come back on for another 10 minutes. So you can see how this is very inconsistent into the space. As opposed to a unit that uses hot gas reheat, modulating compressors, modulating hot gas reheat, you can see how much more stable these temperature and humidities are in this particular case, which is important. Because every time, so why is it important? Well, it's important because if you're changing the temperature and relative humidity in the space all the time, you're changing the VPD all the time. So you're either going from a low to a higher VPD constantly. So it's kind of like force feeding the plant to starving the plant, to force feeding the plant to starving the plant every 10 minutes, right? Because you're not being consistent throughout the whole time that the lights are on. So it's very important. If the plant doesn't, I mean, people don't like to be treated that way. The plant doesn't either. So we have to think about those things. It is definitely a paradigm shift. Dan, I saw you turn your camera on. Did you want to make a comment about that?
I just wanted to chime in and say absolutely. I mean, your last point is it. We don't like, even though the air in the room might be on average 70 degrees and 50%, we don't like to have 55-degree air blowing on us. We don't like to have 80-degree air blowing on us. So a lot of people come to us and they say, hey, the graph that is being shown is what I want, but I can't afford that equipment. All I can afford is the smaller split system, a smaller package unit, small dehumidifiers. How do I get this with that equipment? Well, the drawback is you can't, but you can approximate it again by proper air movement, air circulation. Keep those units discharging high, get that air mixed up before it comes down and enters your plant space. Again, using your fans, so you're not hitting it with cold and hot. If you're using small equipment, one way you can do it is breaking it up into more small equipment, right? So don't put one dehumidifier in your space, put 3, put 4, put 5, so you can break off into different stages of controls. Same thing with split system, use smaller air conditioners. Now, the downside to using multiple small air conditioners is they're not going to last as long, so you're going to have to replace that equipment because it isn't made to run that long. So there's trade-offs in every way, shape, and form here. But for a lot of those of you who are just getting going, look for the smallest, most efficient equipment, do some staging to give yourself better control. And as Jim's going to show us on the next slide, control that air movement. Make sure that the air hitting your plants is comfortable for them.
Well, you know my slides better than me, Dan, because I didn't know that was next. So air movement in these spaces is very important. You know, the plant uses CO2 around its leaf surface in about 4 minutes. So we want to get that CO2 mixed into the space well. Air movement helps avoid the formation of microclimates within the canopy, and it puts the CO2 where it's needed. The leaves should flutter but not be wind blown, ideally below 200 feet per minute. And I'll discuss that in another slide here in a minute. But when you see tip burn, a lot of that tip burn is occurring because of the higher velocity across those leaves. Not enough airflow can lead to proper conditions for mold and mildew to set in. And we need methods for achieving proper airflow, you know, by using wall-mounted fans, inline or destratification fans in the space, in addition to the other means that we have in there. You know, airflow and grow rooms. So, you know, you've heard me say this again, supply air temperature should be above space dew point. It's a rule that has never failed me, and it's one that I would highly recommend that you consider. If the space is at 82 and 58 degrees, that approximately correlates to a supply air temperature of about 68. Air changes per hour. If you can keep those air changes hour up to 30 to 50, that's how many times the air recirculates through the space. 30 to 50 times in 1 hour. It's a lot. But if you can keep air moving that way, either with the HVAC systems alone or with that plus supplemental fans in the space, because you decouple those fans to work and help with that air movement as well. We want to attempt to minimize the microclimates as much as possible. So another thing that's important is to make sure that your supply air and your return air is, if you have both high in the space, some of that supply air is more likely going to short circuit and go straight to the return instead of getting into the space where it belongs. If the supplier is close to the supplier is, if it's 2 or 3 degrees above the dew point, which is 67, and you have an 82-degree space, you know, there's not a lot of temperature difference between that supply air and the space temperature, like there would be in the conventional HVAC system, where, you know, we might want a 75-degree airspace in 82 degrees, or I'm sorry, in 55-degree feeding it. So you have, you know, a 20-degree delta T, where here, you know, we got a much less temperature difference of maybe 15 degrees. The best is to supply high and to return low. This ensures the best air movement in the space. It's very difficult to blow air through a canopy. When the air has a tendency to hit the canopy and be deflected, it's very hard to blow it and have it penetrate through the canopy, especially if you're trying to keep it, you know, between 200 feet per minute and 100 feet per minute when it hits that canopy. You have to draw the air through the canopy to get it to really come through it. In this example, I don't have the supply diffuser shown in this picture, but it does show that the return was down low and it was held up above the benches so that they could roll the benches back and forth across there.
I'll throw in on there too, especially people, I mean, not just cannabis, I mean, but cannabis growing sea of green, berries on tables. We've seen cases where there's completely different microclimates above and below the canopy. Sometimes that's desirable. Most of the time it's not. Sometimes people do want a dryer to prevent root rot and everything like that. Again, adjusting either the flow of your airflow or the placement of your equipment, I mean, is crucial. And that's only something that you develop over time after seeing how your plants are growing and how those microclimates develop. There's a lot of people out there with really expensive sensor systems that can place sensors all over the place. You know what? Just a $300, $200 handheld sensor walking around and checking it frequently will usually tell you pretty much the same thing. So there are ways to do it. It just takes time and a few growing cycles for you to get it down what you really need, and you start to figure out when you need to do something to move air from above and below.
So, hey, Josh, to kind of get you engaged here, I know that in many that you've dealt with a lot of grows yourself, but have you noticed that when the plants are closer to the fans, they have a tendency to get tip burn on them over time?
Oh, absolutely. I've been in facilities that, just had pretty basic fans mounted on the perimeters of the rooms and really didn't account for any of the air movement in the middle. And so they turn them up all the way, and you can literally just see all the tip burn on all the edge plants and really none in the middle. So that's very common. And another thing that I've seen is, during that early phase of growth, when you need humidity in the space, the plants really aren't producing any. So most people have to have a humidifier in there. And I've seen a lot of people place their humidifiers in terrible positions where, I've seen it where the return is literally sucking all the humidified air that they're trying to add to the space, which adds stress to your equipment. It makes it so the room's not really, able to maintain the desired set points. And so, yeah, that is one of the most important things, making sure your equipment is placed in the room appropriately to where your plants are going to be growing.
One of those reasons why, that when that air is hitting that leaf at such a higher velocity, it changes the BPD around that leaf. And so the leaf wants to cut that transpiration off. And that's what causes the tip burn. And just like in this particular case, this is an equation for a swimming pool application. But if you're blowing high velocity air across the surface of that swimming pool, that water will evaporate out of the swimming pool faster. And that's exactly what's happening when we blow high velocity of air across those plants. So the typical rule of thumb is for it to be less than 200 feet per minute or 1 meter per second or less of velocity hitting that plant, so that we don't have this situation occur. Because that air movement is no different than it would be on a swimming pool. Well, let's talk about dry rooms. We've talked about some grow rooms, but let's talk a little bit about dry rooms. A dry room has very little or no sensible load whatsoever in that space. The lights are off, and we're trying to keep it usually between 60 and 65 degrees and somewhere around 50-55% RH, depending on who that person might be that's doing that. So really, we're doing all moisture removal. So if I have 400 pounds of biomass in that room, and I want to remove 88% of that, that's 20 pounds that I have to remove it over 10 days. That breaks down to 1.76 gallons per hour, 14 pounds per hour, or the equivalent of 15,000 BTUs. It's very difficult to do this with conventional HVAC. The return air must be above 65 degrees on a conventional HVAC, or you will frost the coil. And so in this application that I showed you guys earlier with the side stream dehumidifiers, that is why we put on here some sort of heat to keep that temperature above 65 before it hits this coil. Because as these dehumidifiers shut off, we still may need to be recirculating air in the space. We still may need a small amount of cooling to occur. So we want to keep that temperature up above 65. Let's talk about dry room airflow, because I use pretty much the same philosophy with dry rooms as I've used with conventional. We want the air to move through the space very even and equally. Usually we want the supply air is going to be a little bit warmer than the room air temperature. And the reason why is because we will actually pick up some evaporative cooling in that space from the plants drying. So we might want to keep that space at 65 degrees, but we might be delivering 66 degree air to the space to keep it at 65, depending on where you're at in the dry process. We want what's considered laminar flow, so not turbulent flow. We want the air to move through the space and causing as least disturbance as possible. Usually that is less than 250 feet per minute. True laminar flow is less than 50 feet per minute, but 250 feet per minute is a pretty good place to start. And we want that to be even across the entire cross section of that biomass that we have in the space. This is actually one of the first dry rooms I did. And so we have a wall of grills on one side that are supply, and on the other side is a wall of returns. And what we wanted to try to make sure is that we didn't have any dead space in the room. So we did what was called an airflow visualization study. So we used smoke. We set 2 video cameras up at 90 degrees to each other so we could see the vertical movement as well as the horizontal movement. And I'll play this video for you guys so that you can kind of see how that looks. So strangely enough, we determined that we actually had very good air movement. The smoke looks like it's moving pretty quickly, but we did velocity test on these rooms too, and it was below 200 feet per minute. So the visualization of the smoke just looks fast. And here it is on the return side of the room. We did find dead spots in this room, but strangely enough, they occurred in front of the doors. They really didn't occur where product was being held, but they did occur where we expected them to. So we were pretty pleased with how this turned out. Just shut that off because it's just more of the same. So, Cameron, Carmen, do we have another poll results?
Yeah, it's looking like folks are pretty evenly split between the 3 different systems we highlighted: the packaged AC with dehumidifier, the split system with dehumidifier, and the integrated HVAC. All kind of seem pretty well balanced between those 3 systems.
That's great.
There was Jim, there was one question that came in that I wanted to throw out right now. We can save the rest for the end. Someone asked if there's any airflow modeling tools to help plan, visualize how well the air is being mixed. It was originally asked during the flower room discussion, but it applies to the dry room as well. I personally, I've seen some CFD modeling done, but I haven't seen any commercially available software that routinely handles such a chaotic airflow well. Have you seen anything?
No, I haven't seen anything either. I mean, you can certainly hire CFD modelers to do that, but that's why we employ test at the end.
Yeah, I mean, personally, your hand works pretty well. A lighter, toilet paper. I mean, don't throw glitter around the room, although I've seen that done. Just get in there and visualize it, figure it out how it's flowing. But definitely in your dry room, what Jim was doing is essential. One of the biggest things I've seen with dry rooms is air is essentially lazy. So if there's a spot where it doesn't need to go, where it's hard for it to go, it won't go. And that's where your biomass is going to rot no matter what you're trying to dry.
Yeah, you have to have a pressure difference for it to move. And by the way, the smoke, those particular smoke producing devices that we use there were nitrogen, but you can go down to Walmart and you can buy for $50, you can buy a Halloween smoke machine, and they work just as good for demonstrating that, believe it or not, because I have used those too in a pinch. In most places I go, there's always a Walmart somewhere, it seems like.
But make sure it's a room that you can ventilate then, because I did that once in a room that wasn't ventilated, and it took the filters a long time to get that smoke all out. So just a fair warning, learn from my mistake.
I'm not suggesting that we hotbox that room by any means, but
okay. Marble lights.
Yeah. Well, so let's talk about sustainability just a little bit here, because indoor grow facilities use a lot of resources, and I think that we should be cognizant of that and how we can limit those as much as possible. But when you look at energy consumption, 30% of the energy consumed in a grow facility, 30% of that is for ventilation and dehumidification. About 21% of that is for air conditioning, 5% for space heating, 1% for drying. So the total for the HVACD is about 57% total. So it's a big number to think about. So anytime we can reduce that number, we're going to put more dollars to the bottom line. And strangely enough, you would think lighting is higher, but really it's not. It's about 38% of the total energy consumed. So it does take some focus to look at the HVAC to try to reduce it as much as we can. So let's talk about that as a function of wholesale price of cannabis. And these are from 2012 numbers, so they're a little old. But 30% of the wholesale price is used for air treatment and energy cost. And you can look at some of these, how they break down. 18% for lighting, 14% for ventilation dehumidification. Cooling is, 10%. You can add all this up. CO2 is about 3%. So, but the HVAC adds up to about 30%. Talk about some other things. I mean, just doing this is from an actual energy model that was done for an energy rebate. And it kind of follows the other two graphs that we just showed. But the HVAC used 55% was energy savings. This was an integrated system that was modeled against split systems and dehumidifiers. But we're talking about, this is a very big building. So take these values, you're not going to see this on 10,000 square feet of canopy. This was for 35,000 square feet of canopy. We were able to do show a total energy savings of about 48% on this. Given the rebate that was allowed for the utility, it was 10 cents a kWh. And so we were able to get this grower a $956,000 rebate back for energy savings. Pretty big numbers. The other thing that you should think about is lighting schedule. This is something that I harp on quite a bit now. But if you can offset or stage your rooms so that half of your flower rooms are in lighting while the other half is in lights off, you can save substantial amount of money. This really came about from the standpoint that I had a customer that wanted to add 4 more flower rooms, basically double their canopy square feet. And they didn't want to wait, 40 to 50 weeks to get a new service brought in, which is really where we're at these days for electrical switchgear. So what we did is we determined that if they went to a staggered lighting, we could double the canopy square feet and stay in the existing service size that we had. In addition to that, it also saved them about $187,000 in demand charges from the utility by doing that. And that $187,000 was just on the 15,000 square feet of canopy. When we add the next 15,000 square feet of canopy, it would double that. So close to $400,000 in energy savings a year for 30,000 square feet of canopy in the location this was at, which was in Missouri. So just an operational thing like that, and it's not that hard. I think they chose to do like half the rooms would be lights on from noon until midnight, and then the other half would be lights on from midnight to noon. So when they came in the morning, they worked in half the rooms. After lunch, they worked in the other half of the rooms. So it's very doable without having to have a strange, schedule or running 2 different crews. The same thing goes for water, water reclamation just for the condensate. So the water that we are transpiring through those plants comes out in the form of condensate at our HVAC equipment. So we really want to try, if we can, to reclaim that. If you're using 756 gallons a day, which is what this particular case is for 9 rooms, that's 6,800 gallons a day. That's a lot of water if you just put it down the drain and dump your condensate out on the ground somewhere or in a roof drain. So it's something to think about. That's a lot of water that you can save a day and retreat. Take it back to your fertigation room and retreat.
Yeah, I wanted to add to that I've seen people that projects I've consulted on that are not treating that water that's reclaimed from condensate, and you absolutely have to. So make sure you're accounting for the cost of the equipment to reclaim that. Obviously, I live in California, so reclaiming water is very important when you can, but the cost of the equipment, it can be substantial. So definitely account for that in your design.
I think the biggest issue, isn't it, Josh, is getting heavy metals out of it that might come out of the coil from the copper and the aluminum.
Heavy metals, and there's several pathogens that that are in water that a lot of people have dealt with root issues in their crops, and it took me not very long to figure out where that pathogen was coming from, and it was coming from the condensate and being recirculated to the root system. So I mean, most UV bulbs treating that will kill majority of pathogens, but there's some waterborne pathogens that are really small that you do need some treatment to mitigate it. So just always keep that in mind, because I've seen that mistake made with more than 5 growers using condensate. So it is something.
Yeah, we try to employ UV light in the units. It not only helps with that, but it also keeps the coils clean. And then for the heavy metals, there are several manufacturers now that are coating their coils so that we can keep the heavy metals out of that water as well.
Yeah, that's good.
Yeah, I'll just throw in, as equipment manufacturer, we do promote reusing the water. We also absolutely insist that you do some sort of treatment to the water, filtration of some sort. Any piece of equipment, I don't care whether it's e-coated or not, there'll be a plastic drain pan that'll be somewhat porous. There'll be, even if the coils are e-coated, there'll be other surfaces that are metal, and it's just kind of, it builds up. After one pass, there isn't a lot of metal, but if you're reusing, it kind of builds up. And there's plenty of nooks and crannies that don't get properly cleaned where other things can grow. And then there's the ductwork itself as well. It's not the equipment itself, but water gets in the ductwork, grows, comes back into the equipment. So please filter that water. Also, test the condensate coming out of the equipment. Give it a week or two of operating, right? Before you start using it in your operation, let it run for a week or two, because there's a lot of residual oils and other things from the manufacturing process left over. Once that's been flushed out after a week or so, now test the water and see what's coming out of your equipment that you may need to filter or use some sort of other treatment to take care of.
Yeah. Well, let's talk about commissioning and maintenance, something that's very important to me. Oh, we have another poll. Everybody a chance to answer that. And for whatever reason, Carmen, it doesn't let me do it. Maybe because I'm the presenter.
Yeah, you are the presenter.
So, commissioning and maintenance, a lot of this comes down to monitoring, calibration, and making sure that the systems are operating the way they were intended to operate. And the only way to really do that is to test the systems before you actually start using them. But monitoring, you can't manage what you don't measure. You need to collect the data to solve the problems, and collect that data and collect it over time. It's amazing what I can go back, and a month ago, a problem today can be solved by looking at the data from a month ago, and it's very important to save that data. Calibration: if your sensors aren't measuring things accurately, it's very hard to determine what the truth is. I mean, digital thermometers and humidistats get out of calibration, and it may sound funny, but I carry around this thing. It's called a sling cyclometer. Dan knows what it is. Some of you engineers might know what it is, but I use this on jobs. Here. Basically, it's blurring it out. I'm sorry, but you know, you sit there and you wet the wet bulb on it and you sling this thing around and it tells you what the wet bulb and the dry bulb is in the space. There's nothing more accurate than this. And I have proven many digital devices of being inaccurate with that device right there, because it really truly is accurate. But if you're not taking accurate data, you can't use that to really solve the problem. Do functional testing on your HVAC equipment and your lighting and your irrigation to make sure that it is truly giving you what you've designed it or what you've bought it to do. These things are very important. And if you don't do a functional test, is to go out and, you know, and set the temperature and humidity and put the water into the space and make sure that it's functioning the way it was intended, that dampers open when dampers are supposed to. If you get a high level of CO2 in the space, did the CO2 evacuation system turn on? Did the alarm go off to tell you that there was a problem in the space? You know, these are very simple things to do. I do have an issue with CO2 evacuation systems, and I saw, Dan, that you answered one of those questions, but I won't get into that, you know, on my soapbox about it. But CO2 is not a dangerous gas. It's not poison. You know, it's not going to generally kill you. It just displaces oxygen. So looking at maintenance planning, you know, you got to have a budget. You got to have that in your budget to do your maintenance. You got to schedule your system's downtime. What I tell folks, what I recommend you do is that when you're going to take that room down for harvest, you call your HVAC service tech and you have him go through that equipment and make sure that it's going to run for the next, you know, 8-9 weeks, whatever it is, through flower. They can test amp draw on motors and compressors, and they can check refrigerant charges. They can check temperatures. They can check all those things, and they can identify if something may break in that next group. Because the last thing you want is for it to break when you're in the middle of that cycle. You don't want, and guess when it's going to break? It's going to break on Christmas morning. It'll break when you don't want it to break. But if you do some preventative maintenance, you can reduce the amount of times that things do break. Schedule those resources with your vendors. Keep common parts and consumables on hand. You know, if you can keep a spare motor on hand, keep a spare motor, a condenser motor fan, a compressor, you know, a controller, you know, all those things. Try to keep them on hand so that you're not waiting 2 weeks in this lovely, you know, supply and demand that we're living in with lead times, you know, stretching out very long on parts and equipment. You know, you may be waiting 4 or 5 or 6 weeks to get something that if you just had it on the shelf, you have it, you can use it right now. Access to equipment. This is probably one of the things I don't like the most about doing decoupled systems that are actually located in the space, because without doubt, that dehumidifier or that AC unit is going to break, and somebody's going to have to get to it to maintain it. And they're going to have a bunch of tools around their waist as they're climbing the ladder. And the fear I always have is those tools falling out and smashing into a plant, or them falling and smashing into the plant. I mean, try to locate that equipment so that it's in an area that can be accessed easily, so that you don't have to run the risk of your plants being damaged in the process. The most important thing, and Dan, if I let him, he would harp on this tremendously, but filter maintenance is very important. I like to try to put the filters in the space so that you actually see when they're dirty. When they're in the piece of equipment, they're out of sight and out of mind, and you have a tendency to forget about that. But when you start getting low airflow through that unit, the coils will start frosting. The main culprit to that is generally a dirty filter. So keeping those filters clean is going to get you closer to the finish line than not. Making sure your drain lines are kept clean. Don't use, you know, clear plastic for your drain lines, because guess what? Algae will grow in them, and that just makes them get dirty faster. schedule your routine maintenance and clean, clean, clean. Common parts and consumables, we're hitting on that again. When you're spraying your rooms down, turn off the dehumidifiers and turn off the AC. It'll help save some of your filter replacements if you do that. Room integrity. This is something that's been coming up on a lot of projects here lately, and it's rooms not being sealed well. That room needs to be airtight. It's very imperative because you don't want to, in the wintertime, leak moisture out of the space, especially when lights are off. And in the summertime, or in the higher humidity days, you don't want to be gaining humidity into the space either. So keeping it airtight. All that is energy that's leaking out of the room. The vapor pressure travels from higher to lower always, and it travels at nearly the speed of sound. I mean, it will. I forget the exact numbers, but it's like it'll travel 100 feet in 4 seconds. Moisture moves quick, and it moves against airflow. It's worse in the night when the lights are off and your plants aren't transpiring, and it's worse in winter climates. Dehumidification without compressors. These are pictures from an actual blower door test that we did on a job that was leaking more moisture. We weren't running any cooling at night to keep that room dehumidified, and it was over dehumidifying. We had 624 CFM of air leaking out of that space, which in this particular space was almost 1 air change an hour, and we were losing 84 pounds an hour of moisture out of that room at night. Dan, what dehumidifier do you have that does 84 pounds an hour?
A lot of them.
Right. So like what? A 7? No, 7. You probably a 130. It definitely will do that, right?
A little more, yeah. That's quite a bit.
Yeah, it's quite a bit of leakage. And this didn't take. I mean, you would say, oh, well, okay, you figured it out. No, this took like 4 months to figure out. This wasn't something we just figured out in a day. You go through these steps of eliminating things to get to where you finally figure out, well, that didn't solve the problem. That didn't solve the problem. That didn't solve the problem. Wow, I wonder if that room leaks, and then you got to schedule the blower door test. And then you got to go back and seal everything because you can identify the problem, but now you got to fix it. It would have been so much easier to take care of during construction. So very, very important, room integrity.
The best way to investigate things like this, paper and pencil. Take notes, take logs every day. What's the temperature and relative humidity outside? What are you maintaining on the inside? And what problems are you seeing? If you start seeing problems that only occur on really hot and humid days or really cold and dry days, then you know that it might be your room integrity. If it has nothing to do with the outdoor weather, well, now you just got something goofy going on the inside.
Wow, 52% say you offset your lighting, and that's great. 20% don't. I mean, offsetting your lighting, if you have multiple rooms, is the absolute easiest way to save energy. It doesn't cost you anything to save energy. And I would highly encourage you to investigate changing your procedures to do that. That's the low-hanging fruit. That's the lowest of the low-hanging fruit. Thanks. Lessons learned. When you've done a lot of projects, you learn a lot of lessons, and you try to carry those forward into other projects. And then you get brought in to help troubleshoot projects, and you can figure this stuff out. But if we were to go down this list, and Dan and I and Josh, got together and we came up with a list of things that we thought were important to mention. And as we mentioned in the very beginning, the business plan drives everything. Please use your business plan to plan your rooms out appropriate. Operate and design your facility around the plant. And I would always recommend not sacrificing quality for quantity. If my customer said, I only have half of the money that it takes to build this, I would say build half the rooms. Build half the rooms and then build the other half with the revenue that you're bringing in from those. Always build for quality, not quantity. Seal your rooms airtight. Always remember that not all hot gas reheat is the same. If you're going to use that technology, make sure that it is being applied properly. Don't use internal liner in your ductwork. If you get an infestation, it's really hard to get it out of that liner. You end up having to usually rip it out and replace it, or not replace it at all, just rip it out and insulate your ductwork externally. Make sure equipment will operate below the lowest outside air temperature. And I went, Dan, and looked at California's winter design temps, and there are at least 36 cities that get below 30 degrees at night in the wintertime. And most of your manufacturers will tell you that their equipment doesn't operate well below 50 degrees outside. So make sure that your air equipment has low ambient controls on it so that it can operate below the lowest outside air temperature that you expect. Schedule lighting to minimize demand charges. As we said, half of you guys are already doing that. That's great. The rest of you, I'd highly recommend it. And make sure there's good mixing of air in the space. You know, you really, really want to have good airflow. And then deliver that air at 2 degrees above dew point if you can at all do that. Dan, Josh, did you guys come up with any more?
I'll just, you know, on the outside air temp, I mean, make sure that your equipment can handle the conditions you're going to give it. Air conditioning equipment is built to normally just operate in the summertime, not when it's cold outside. Talk to the manufacturer before you buy it, see what tips and tricks you might have to do to make it work for your situation. Go ahead, Josh.
I was gonna add, just because in California there's a lot less new construction, there's more retrofit of older rooms and facilities. Anytime you're making changes to these pre-existing rooms, really make sure you're taking a holistic approach. LED lighting's come a long way since rooms were built. However, when you're reducing your wattage in the room and your equipment, your HVAC equipment is now significantly oversized in a lot of cases, you know, you're going to have a lot of short cycling. You're going to have, you know, equipment that really isn't ideal for the space anymore. And you're either going to have to make some changes to the equipment or the control side. And a lot of people aren't thinking about that when they're planning on, you know, doing an acquisition of a grower, you know, maybe, you know, just planning out their design of these rooms. So really look at it 100% holistically, not just changing one thing that you see is not ideal, because you'll run into problems, I guarantee it.
It's just as bad to oversize equipment as it is to undersize it.
Oh, absolutely.
And equipment is expensive. So if you're giving your engineer watering rates, make sure that it's watering rates that are real, that is the water that is coming through the plant, not going down the drain, because we don't care about the water that goes down the drain. We only care about the water that's delivering the nutrients to the plant and transpiring through the plant. And that's the important part.
Yep.
Carmen, were you going to talk about these program offerings, or was Brian going to do that?
I'll just run through them really quickly. So there's a handful of programs that are available through PG&E, and they're always evolving. So get involved, talk to your representatives. This slide deck is going to be available later, and you can go through all of these different ones. There are specific ones for CEA and cannabis. So there's specific pages that you can click through there to go to that. And then we also have the AESAP, which is specific to agriculture. And so these have specific programs for cannabis and specific programs for CEA. There is funding out there. You can take advantage of it. Do it. And then back to you guys with your actionable takeaways and Q&A.
Yeah. So do we want to just go right into to Q&A then?
Yeah.
I mean, some very, you guys can read. I know that we kind of ran a little bit longer than what we had planned, but I always recommend to choose design and installation professionals with experience in this industry. It will save you a lot of headaches later. Just like you wouldn't want to get someone who is an expert in cannabis designing churches. You don't want somebody that's an expert in churches designing your cannabis facility. Schedule a blower door test, and PG&E can help with that. But I'm telling you that I always put in my jobs the blower door test requirements, and then if they don't meet those requirements, then the contractor has to seal it and pay for an additional blower door test until they pass. So that's a huge incentive. Do pre-construction meetings and talk about all those sealing details. Just because they're in your drawings doesn't mean that everybody paid attention to them, but it is important to make sure that they understand it needs to be done. Review your maintenance schedules, change filters, and clean. Those are the two most important things that anybody can do. Plan comprehensive maintenance during harvest. Avoid clear tubing in your fertigation systems. I mean, that should be a no-brainer, but man, I walk into a lot of facilities with this green mucky looking tubes, because they use clear tubing. Check your circulation flow flow patterns and make sure that you're getting good airflow and good mixing in the system. And of course, check your equipment and your sensors for calibration.
Yeah, and I can't stress from being an operator on having that planned maintenance. You should have your harvest schedule planned for the next 5 years if you're planning on being in business, and having that planned out in advance so you don't run into issues, because they're going to come up. Equipment fails. A lot of this equipment wasn't meant to run this way. So having some preventative maintenance that you do on a schedule. A lot of these people that are doing maintenance on your equipment, they would prefer to have a schedule so they don't have to come out on Christmas. And believe me, I've had a Thanksgiving that I almost burnt my turkey because I had to run to a facility and fix an issue. So definitely plan it out ahead of time.
A couple of years ago, I spent Christmas morning talking to a customer and how to power cycle his chiller that went off on Christmas morning. Not only was he out there, but I was getting the raised eyebrows, here at home. So it's always best to do it, on a regular work day during the hours.
Yeah, absolutely.
I'm going to quickly mention, so one of the other PG&E reps wants to remind people that they have a tool lending library, and SCE also has one where you can rent a whole bunch of tools and energy measurement tools, including CO2 temperature, relative humidity sensors, and blower door equipment. So you don't have to necessarily go out and buy this. You can work with your utility. And then I quickly want to let one of our participants talk who has their hand raised. Prahlad, do you want to ask a question?
Hello, no, I think that's by mistake.
Oh, okay, that's fine.
Sorry.
All right, so how important is energy efficiency to you as a grower, Josh?
I mean, it's extremely important, and it's become over the past 4 years, as it's competition and pricing in California has just changed dramatically. It's up there on the top 3 most important things when you're operating. Obviously, labor is going to be a huge cost, and reducing that, but yeah, it's so important. I don't know how to stress it more for people, especially if you haven't been in this space and you're looking to get in. That first time you get that utility bill from a decent sized indoor facility, your heart gets it pumps a few more times when it's your money that's paying that bill. So anything you can do to reduce your energy costs in the beginning will make operating. It'll make you more competitive. It'll make it so you can actually have a business that's around in the future. And some people's business goals are not they're to do it quickly. But for me as a horticulturalist and someone who loves the plant, I don't want to be involved in any business that doesn't plan to be around for a long time. So if that's your goal, really think about that when you're picking your equipment.
Yeah, thanks, Josh. And then I want to ask Dan, what are some simple things that growers can do to maintain optimal equipment efficiency? Simple
Sure.
things.
Simple things. I mean, the first is the selection of equipment. I'm a big proponent of the KISS philosophy, right? Keep it simple, stupid. I can design you the most complicated system, most wonderful system with the most incredible controls. But when you're a two-person operation, one CFO, farm manager, the other one's marketing and janitorial, you don't have time to learn how to use the most complex system. Keep it simple, keep it something that you can operate, that you can clean, that you can maintain, that you can keep running as close to new conditions as possible. And of course, if you haven't caught it by now, that means change your filters and clean after harvest. Get everything washed out, treat it as if it was a food processing facility. Schedule regular maintenance with HVAC professionals. Find a, just like Jim said, find a design professional to help you design it that understands cannabis or CEA operations. Also find a contractor that can help you do the usual tune-ups, that understands the equipment as well and how you're using it and why they're not going to be looking at a typical piece of equipment run under typical conditions. Those are the simplest things.
Right. And then there was a question that was sent in earlier about using an HVAC economizer to use cold ambient for cooling instead of heat pumps.
I'll grab that one. So I believe that was someone from outside of California. So this came up, and actually this came up again, I see from Troy Foster. And Troy, I'm going to get a hold of you afterwards to continue the conversation about CO2 enrichment. Both California Title 24 did not mandate the use of economizer as well as a number of other states, because typically when the lights are on, we're going to do CO2 enrichment to 1,000, 2,000. I've even seen 4,000 parts per million. So the use of economizer basically dilutes that CO2 and it's not productive. I have seen water side economizing. I've seen a few cases with using air-to-air heat exchangers under cooler environments to basically remove heat from the space. But typically it's a very difficult sell to get across unless you're in a very far northern climate. I mean, we're talking Montana, Minnesota, Canada, or above.
And then do any of you have any closing comments for our participants? Last thoughts?
Besides clean and change the filters?
Yeah. 2 degrees above dew point, right? I mean.
Yep. And my closing comment would be, again, keep it simple. Make sure you understand the limitations of the equipment that you pick. Make sure you know how to operate your system. Again, use the paper and pencil. Take as many notes as you can. Look for trends. So that way, hopefully that utility bill keeps going down, and use the professional services available. A number of you asked about, what's a good baseline for rating my equipment against. Well, Carmen and Bryce can talk to you about what RII has to offer for looking at comparison tools. Look at yourself over time. Am I getting better? Am I getting worse? You should hopefully always keep getting better.
Yeah, and I'll add just that holistic approach to designing your room to actually be able to achieve the temperature, humidity, CO2, lighting set points. Really make sure that everything's working in harmony, because your plant will notice when things are off, and you'll notice. And if you want to avoid those catastrophic failures that can literally ruin a business overnight, think holistically, get the right equipment, and operate well.
That reminds me of another one. Take a look at your equipment. If the humidifier and dehumidifier are running simultaneously, you're not doing something
Yeah,
right.
something's wrong.
Air conditioner and heater running simultaneously, something's off.
Yep.
You don't drive your car by pressing the gas and feathering the brake to slow yourself down, right? Think about it. Only cooling or heating, only dehumidification or humidification.
Yep.
Well, on that note, I will say thank you so much for attending, and the recording will be available as well as the slide deck online later this week. And we appreciate everybody's knowledge sharing. Thank you to Jim, thank you to Dan, thank you to Josh. We really appreciate all of your thought leadership, and thank you to all of our attendees.